Thank you very much. Thank you for the opportunity to speak at this wonderful event. And thank you for being here. So the first morning speaker thanked everyone for coming early. I'm not sure if it's difficult to come early or after lunch. So there will be no persistent homology in my talk. Although we use it daily, I think that it might be a good idea to steer the conversation a little more towards geometry this time, because there are interesting things to do and interesting ideas to consider. So I hope that the ideas themselves will persist. So this is joint work with Shayan Mukherjee and Tingran Gao, from whom I've learned quite a lot about classification of shapes, which is a very interesting class of problems, which is beautifully placed between traditional machine learning type technology. It connects with statistics, and of course it has a lot to do with topology and geometry. So I think that there is a class of examples that are worth considering. So basically the idea is this: you have a class, a set of objects. I'll show you examples, but just think of your favorite geometric objects, like your favorite Lego figurines, for instance, or whatever it is that you like to do but are afraid to tell anyone. So I don't want to look inside your brains, okay? So imagine that there are transformations that connect them somehow, okay? So those transformations will come from a particular group or maybe a collection of groups. So the objective of this is to learn the set of group transformations that would transform each object as well as possible to another one. And of course, but precisely what you mean by transformation will depend on the particular geometric problem that you are trying to solve. Okay? So if it is possible to find a sequence of group elements that allow for a good matching between objects, then you can say that the set is synchronized or synchronizable. That's what it means. Okay? So the goal is that if someone gives you a class of objects, the goal is to find this matching sequence of transformations that will produce, if you like, a globally consistent arrangement of those transformations. The main ideas for this work come from manifold learning and data sets sampled from manifolds. But what we discovered in the process of this work, that you do not need this assumption, that there are many interesting ideas that you can use on pretty much any any reasonable data set of this kind. So this is, if you like, it has to do more with rigidity of some sort than smoothness, which is good. So let me take you through a list of examples, just to show you that this is interesting. So this is one of my favorite ones. This is taken from a set of lecture notes by Bandera, but really many of the ideas here come from the work of Amit Singer and co-workers, and this is one of them. Cryo-Electron Microscopy. So if you want to understand a three-dimensional structure of a molecule, traditionally what people did is you would make a crystal out of a set of your molecules, shine X-rays through that, and study the resulting diffraction patterns. For instance, this was used to discover the double helix structure of the DNA and many other things. But there will be substances that will not lend themselves to this procedure. You will not be able to make a crystal out of pretty much anything you want. So this is actually really, really inventive. So what you do is you take enough molecules to create a single molecule layer, okay? And then you cool them down until they stop shaking. Well, they will never stop shaking, but they stop shaking enough to match the resolution of your machinery, okay? and then you just take a snapshot. So it's really no different to taking a conference group photo. You know, you just cool everyone down for a nanosecond and then just blind everyone, and then we think that everyone was standing there for hours, not moving. So that's really the situation. But what's really curious is that what you get is a set of two-dimensional projections of your molecules along random directions. That's essentially what this procedure produces. And then the question is, can you actually use the information provided by this set of two-dimensional projections to reconstruct the three-dimensional structure of the molecule? So a really neat idea by Singer and his co-workers was to regard this layer of molecule as just copies of one molecule rotated through three-dimensional rotations. So the problem is, okay, can I connect my molecules through three-dimensional rotations so that I can reproduce these matching, X-ray images? There is an awful lot of wonderful mathematics involved in this, but part of the problem is exactly how you arrange those molecules, connecting them through three-dimensional rotations, okay? So that's part of the motivation for this problem. Those of you who study shape analysis may have seen these types of pictures before. And again, if you want to study, for instance, evolution of animals, assuming you believe in evolution, you might be looking at objects like this. These are teeth. And you might want to trace changes of some markers as you go from one species to another species, and so on. So again, the question is, how well can you match them? And again, the level of accuracy of your matching will determine what you will take to be equivalent or the same or not. You see, this is where the classification problems arise in these kind of sets. I'll come back to this later. So here is a set of photographs. It's Alan Turing plus noise. So this is a standard set of problems that you may have, for instance, photographs, but you may have other objects which are given to you subject to some uncertainty or some noise. And again, the question is, can you actually identify connections between these objects? Can you create a family of transformations like the orthogonal transformations in this case, plus some random noise correction that will connect these objects? Well, if you can do it within a reasonable accuracy, then you can say that you do have copies of one object. If you can't do it, then perhaps there's the suggestion is that there is more than one class of things inside your set. So here is an artist impression of of the previous slide, just to point out something that, as I said already, this classification will depend on the class of transformations that you agree to use. So you can connect up all of these pictures except one, because all of the pictures that are connected have been obtained from one another by rotation, whereas the last one is a rotation and a reflection. So you see, again, so this shows if you didn't care about the determinant of your transformation, then of course all of them would be connected. But if you do, then now you know that you have one gigantic orbit of something and one element which is not connected to them.
Why some are not connected in the connected component?
I'm sorry?
Why some are not connected by
Right. Because it may just not be possible to figure out a corresponding transformation with a reasonable enough accuracy. That's all I'm saying. I know that they are all connected because I made the slide by rotating one through rotations, but that's cheating. What I'm saying is that in real life, like these projections of of molecules, you may simply not be able to figure out a transformation that connects them. Okay? Right. So this is then going to be our setup. We will take a set of objects and a set of group actions, and we want to, as an output, we want to obtain a partition of this set into orbits given by the group action. Okay? I will make an additional assumption because that's going to be useful in practice. We would like to connect objects by an element which is reasonably close to the identity in your group. Okay? This again is trying to establish similarity and not whether some really sophisticated fancy transformation can be forced to exist. But this can be relaxed and so on. So the examples that I gave you fit into these general headings: geometric, morphometric, geometric processing, multi-commodity flow, network alignments, and cryo-electron microscopy that I already mentioned. And there was quite a lot of interest in these subjects. So in the last few years or so, starting with papers by Singen and Wu on manifold orientability, which can be interpreted as synchronizability for the group O1. Angular synchronization, vector diffusion maps were designed in parallel with these problems. And then you can see a long list of other problems: collection shape matching, which has to do with the permutation group, and cryo-EM. It's the various the group of orthogonal transformations and its various subgroups and so on. And our little contribution here, which is on the archive and has been submitted. So I will touch upon three points of view in one example. So one, that will place this synchronization problem in context of other mathematical methods. So one, we will talk about holonomy and the corresponding fiber bundle structures. That this is an interesting new phenomenon. We will talk about this through the point of view of cohomology, but this is just the standard de Rham type cohomology and the corresponding twisted Laplacian. I will show you briefly an algorithm that we have created to deal with this, and then we will talk about what primates eat. So that's the plan. That's the plan of. So let's look at the setup of this problem. It's natural to start collecting the information about transformations between objects into a graph. So whenever you can establish a transformation between two objects, you create an edge in your graph, and then there are two pieces of information. So I'm assuming that I have a graph with some vertex set and an edge set and a group G. A function on the vertex set with values in G will be called a vertex potential, and a function on edges with values in G will be called an edge potential. This is to match it with the terminology established in some of the references I said. I'm assuming that the edge potential is symmetric, so if you traverse the edge in the opposite direction, the group element you assign to it is the inverse of the one you've assigned previously. That's actually going to be quite useful. And this can be this setting can be extended to functions with values in G modules, and I will come back to this later. So here's the question. Given an edge potential, does there exist a matching vertex potential which is compatible with rho? So compatibility simply means you have an edge with a group element attached to it. You have one vertex with a group element and another. So simply, as you take this group element and ask, is this actually the same as the product of what you find on the edge and the group element at the opposite end of this edge? If it is, then those two potentials are compatible across the edge, and they are compatible if they're compatible across every edge in your graph.
But these edges, they correspond to some paths in Cayley graphs, right?
No, these are paths in the graph. They are not necessarily paths in the Cayley graph of the group. Okay? Although the group itself might, the Cayley graph might be an example of what we have in mind. Yeah.
So you can ask the question if you fit the previous one. So you have this equation there, and so what, you have rho ij and rho ji, that's the inverse.
Yes.
Oh yeah, okay.
Yeah. Yes, that's. I probably flicked through this too quickly. Sorry, I must have pressed this twice. Apologies. Yeah, I believe okay, so this is my setup. So the edge potential is symmetric, and this is compatible potential. So somehow skip this, but this is really the definition of my compatibility question. So I really want compatibility. So if you go from here to there across this edge, the group element you brought with you is the product of the two that you find en route. Okay, so the synchronization problem is this question. If you have an edge potential, does there exist a vertex potential which is compatible with rho? Okay, so that's, how do you answer this question? How do you know that you have one? I mean, how do you test that you don't have one? What would you need to do? Right? Before I move on to, let's just remark that if someone actually gives you a vertex potential, then constructing the corresponding, a matching edge potential is actually very easy. Okay, because this is all you need to do. If every vertex of your graph has a group element attached to it, then these are the matching edge potentials that you need to define. This actually is going to be quite useful in what follows, because indeed, that's exactly right. Yeah, so there is a limit to this, to how you can use it. So let's see. Okay, this is the next one. Right. So some very simple observations first. So if you take a path, so it's very, very natural to start thinking about these synchronization problems in terms of walks along your graph, right? I start here, I walk to the next vertex, and then to the next vertex, create a path which is just a sequence of edges connecting two vertices. But here's a very simple thing. If you take your path and multiply the group elements that you find along that path, that's just a map from paths to your group, which has two very natural properties. If you traverse your path in the opposite direction, reversing every edge, then the resulting group element is the inverse of the one connected, is the inverse of what you had previously. And you can, when you concatenate paths, then clearly you can multiply the group elements associated with them. Okay, so there is a very natural transformation from paths in this graph to your group, which is a group homomorphism in this sense. So, all right, so the very natural way to check if your edge potential is synchronizable is to go around the loop and see what happens when you come back to where you started. So this makes the space of based loops interesting. So before we create an algebraic structure out of that, I need to add the trivial loop, so the loop where you don't go anywhere, and you assign to this the identity element of your group. So this, in fact, this assignment gives you a map from based loops in your graph to your group, which modulo simple checks creates a subgroup of the original group, which is the holonomy group at the vertex. Okay, and it's a simple thing to check that if you have a connected graph, then two holonomy groups at two different vertices are isomorphic. You can just like in the standard homotopy theory. Okay, and here is a very simple test of synchronizability. If you have a connected graph and an edge potential, then there is a compatible vertex potential corresponding to rho if and only if the holonomy group of some and hence every vertex is trivial. Okay, so this shows you that this is somehow that this idea of synchronization matches very naturally with some very standard and quite simple ideas that we know from homotopy theory and so on. But there is more. And the basic idea is this. This is actually quite fun because this is again reinforces our feeling that it was right to look at paths, because how would you define a vertex potential? I'm sorry, a vertex potential that matches your edge potential. Well, you start somewhere, assign the identity element to where you are. And for every other vertex, you simply assign to it the vertex, the group element that you get from traversing the path that connects you to that. What if you take a different path? Then, of course, the path out and back is a loop. But we now know that the holonomy of every loop is trivial. So this very simple calculation shows you it doesn't matter which way you go. Okay? So this is why it's so very natural to connect this synchronizability to holonomy. But there are various corollaries that flow very naturally from this, and one of them is the following. So if you if you have a synchronizable edge potential, then clearly, well, we now know that the holonomy of every group is trivial, so therefore the holonomy of every triangle, if it exists, is also trivial. But this condition that going around triangles produces trivial elements is actually known in the shape study, in shape analysis study, where these three conditions together, that the potential assigned to a vertex is 1, that the edge potential is symmetric and satisfies this triangle identity. These are called these are called co-cycle conditions, and here's an example of a paper by Huang and Guibas from a few years ago on shape matching with something like this was used. So we recovered this very naturally, but there is more that we have found, and this is actually quite interesting. You see, on the left here we have our graph, and we now have, you see, each vertex represents an object that in our set. But now the objects, the points, if you like, in our set have non-trivial structure, and it's useful to record this structure somehow. So you can give yourself a fiber above each vertex, which is a space appropriate to describe the geometry of the objects that you are considering. If you have a box of teeth, then R3 might be a reasonable space. But you can see that this suddenly is quite flexible. If you are trying to match objects with really non-trivial geometry, these fibers can be fairly complex spaces in their own right. Okay, so those co-cycle conditions, those of you who read Steenroth's book on fiber bundles will know that if you have a topological group acting on some space and a system of coordinate transformations on another space X, which satisfy these co-cycle conditions, okay, so you have a covering of your space X and a matching transition functions that satisfy these co-cycle conditions, then this means that you have a fiber bundle with the base space X and fiber Y, where the group G acts as the group of coordinate transformations. So this is something that we have constructed just by trying to decide how we would solve the synchronization problem. Okay, the solution of synchronization problem presents to us a bundle on on the graph that we have constructed. And right, so the graph, if you like, so the connection with Steenrod's theorem is quite interesting. Essentially, the graph is the nerve of the cover that creates the bundle, and we've forgotten about the space. We have forgotten about its open cover. All we have is the nerve, but this bundle still survives. I hesitated to say persists, but it still survives. Okay, so the theorem that summarizes these initial considerations can be stated as follows. So we have a group, and we have a connected graph, and we have this symmetric edge potential. Okay, so now we give ourselves a set of stars for each vertex. For each vertex, we consider an open star. So an open star is simply, we now regard these as geometric objects. So it includes everything, this edge, but not the vertex at the other end. Okay. So here's the star of a neighboring vertex. Okay. So now we can take and overlap two such stars, and these two stars overlap along the unique edge that connects the two vertices. I'm assuming the two vertices are connected by at most one edge, and this is the intersection of the two stars. And rho is is the edge potential. So rho is synchronizable if and only if the bundle that we have created is a flat trivial principal G bundle. And these extra conditions come from the fact that there is a very natural equivalence relation for synchronizable potentials, because if you can find one, there is a very natural action of the space of functions on the vertices with group values, which gives an equivalence relation of those solutions. And putting together, they create a flat trivial G bundle over the graph called the synchronization bundle. This is precisely essentially the bundle with trivial holonomy. All right, that's what it is. Curvature can be detected by non-trivial holonomy. Okay, so how do we fail? So far we have these bundles. How do we fail? So the compatibility condition for edge and vertex potential is this simple equation. So assuming you are in a situation where this arithmetic operation makes sense, so for instance, the functions take values in some module over G rather than G itself, then this difference makes sense, and it measures, it provides an obstruction to synchronization. And how do we quantify them? So if we have a normed vector space, so that the group we are considering sits inside this general linear group, and a function from vertices to that space, then a failure of the existence of synchronization, or how close you are to synchronization, can be measured by this quotient, which Singer and others called frustration, and I like the word frustration. It's somehow obstructions can be called frustration. So you can see that if this, of course, is 0, then this is 0. In general, if you fail to synchronize, this gives you some number, and your object is to find a minimizing function, a function for which this is minimum. In analogy with graph theory, it's tempting to write this as a Rayleigh quotient, where there is in a product given by something that you can deduce from these, whose form you can deduce from the formulae, and we can call the graph connection Laplacian, which is simply given by this formula. But this object deserves a closer look, and this is what we are going to do. I mean, where does this come from? And why should we be able to call this the graph connection Laplacian? So the setup is going to be like this. So we are now going to construct a de Rham type complex over the graph. So we are going to have zero forms, which is just functions from vertices to some field over which your group is defined, and one forms, which are simply going to be functions from edges, which are skew-symmetric over edges. So then the standard graph type de Rham complex works like this. You can go from a function on vertices to a function on edges by simply taking its gradient. So that's calculating its difference across each edge. There is something that goes, an operator that goes back the other way, which can be called divergence, which converts a one form into a function on edges by simply summing it at a particular vertex, summing it over all adjacent vertices. And this is the complex that gives you the standard Laplacian. Okay? So when you actually compose them, when you compose these two operators together, then you do get precisely the graph, the Laplacian, which is known to us from graph theory. So it is really the composition of the gradient with the divergence. In our case, what's very natural to do is to twist the differential. The gradient, as you go from one end to an edge to another end of this edge, you simply twist by the group element that's provided to you by the edge potential. And it's tempting to call this the graph Laplacian, the connection Laplacian. And you are right. That's really how we would like to define our differentials. Okay, so this is the twisted differential, and this is the corresponding divergence, and the Laplacian is the composition of the two. There is a slight problem in that this doesn't respect the skew symmetry that we requested. Okay, so these are the proposed operators, but d rho is not skew symmetric. Okay, and this very simple calculation illustrates that. So we need to complicate things just a little bit, and again, thinking through the rudiments of bundle theory helps here, because what we are discovering here is that this expression can be regarded as a local expression in the system of coordinates given by a particular trivialization of a one set in the cover that trivializes our bundle. Only we don't see the sets, we only see vertices. But if you actually pretend that this bundle comes from some covers of some space you can't see, then again, you can actually use the transition functions to if you like, glue forms from one coordinate neighborhood to another, and then everything is fine. So in summary, we can go from this purely combinatorial Laplacian to this twisted combinatorial Laplacian, where this new item simply says that you need to remember that you need to construct sections of the bundle that provides forms using the transition functions given by the edge potential. And after that, this is actually quite interesting in that the associated Laplacian allows Hodge-type decompositions like this, and it's a really simple exercise to check that solutions to the synchronization problems sit inside the kernel of this differential. When we look at this differential, then of course the edge potential and vertex potential are compatible if f is in the kernel of this operator. So this is interesting because this shows that the synchronization problem has an interpretation which is very naturally connected with the standard Hodge type considerations of a de Rham type complex on a graph. Okay, so this is what we have. The solutions to synchronization problems sit inside the kernels of these operators. Right. So now about learning group actions. So the goal here is to make this a little more general, and we now consider a group acting on a set X. We want to partition the set X into disjoint subsets, essentially orbits of this action, so that on each component, the action is cycle-consistent in the sense that I have described before. Okay, so this is our goal. And there are numerous examples of this. So for instance, when you have a vector space and you have a group acting on it, you may seek a direct sum decomposition of that space into irreducible representations. So this is something that you know very well. So it's when you have a group acting on something, you try to find the most primitive representation of that action. There are numerous other examples of how this might be useful. So imagine that you just have a set of points and the function from x to plus and minus 1, which you can interpret as giving each point a spin, which either points up or down. And then the group acts on this by just flipping the spins from up to down and conversely. So imagine that we don't know the spin of each assigned to each point, but we know the group actions. Then we will be able to decompose this set of points into two disjoint components of opposite spins. We will not know which is up or down without just having a closer look, but we will be able to find that there are two different spins. And there are this is a slightly more precise list of references. So the case of the orthogonal group acting on itself and the orthogonal group acting on the unit sphere has been considered by Bandera, Singer, and Spielman. Synchronization of rotations, again, this arises in the context of this cryo-EM work. It's by these guys, Singer and others. Orientation detection, which is very close to what I just described, because that's, again, if you want an orientable, if you want to detect if your space is orientable or not, that's what you will need to do. Cryo-Electron Microscopy again, and global alignment of three-dimensional scans with the rotation group has been considered a few years ago. Okay, so the algorithm that we have for this works as follows. Its input is a graph, an edge potential, and we provide a number of partitions. And output, we want the number of partitions, and the output is a number of, a set of partitions of our original set, over which the group acts in a synchronized way. Okay, so we initiate the algorithm through solving the synchronization problem for this particular row, compute the correlation between points according to this formula. So this is a kernel that comes from a particular norm given by how close our solution is to synchronization. Then cluster spectrally, use spectral clustering of this weighted graph to get this partition. solve the synchronization problem within each partition and glue the local solutions to get something global, and then repeat for as long as you need to go to get the frustration within an acceptable interval from well, to win the amount of error you are prepared to live with. So let me give you one or two examples of how it works. So lemurs, sorry? I know, yeah, it's just, well, lemurs, you have to talk about lemurs, right? It's just, yeah. Oh, Sergei is a meerkat. I'm sorry. I think Sergei is a meerkat. Well, but the next example is about meerkats, so it's lemurs are, of course, featured in the series of movies about Madagascar, you know, not documentary, but the animated strip. So, yeah, okay. I didn't know that about when I started working with Cheyenne and Tingran, but Duke seems to be the center of the universe when it comes to lemurs. They have a fantastic little lemur zoo there, and so if you're ever in Durham, I strongly recommend that you go and look at lemurs. The variety is quite striking. So, how many people have seen here Madagascar movies? What I mean is that, okay, so King Julian is a lemur, and Mort, I was really perplexed by Mort. Mort is his sidekick. I thought it was a different species, but Mort is also a lemur. And they have a lemur that looks like Julian and looks like Mort. So you see, this is what you learn by data analysis, you know. But you look at teeth. To be precise, you look at molars of these animals, and these are complex objects. So it requires a tremendous amount of work to just take one tooth and for instance, create a mesh that describes it. But then you also need to mark some characteristic points on each tooth. So there is an awful lot of human input into this work. So not only do you have this mesh with 5,000 vertices and 10,000 faces, but you also have landmark points which are marked by people, by hand. Okay? So this set might look like this. It's a version of what you've seen before. So you will have some teeth with landmark points. And, well, okay, are those teeth similar to one another or not? I mean, you eyeball them, they look like teeth. So, but it turns out that right teeth are different to left teeth, and that's deliberate. That makes it easy to actually eat. So that's good. But your left teeth are different to your right teeth. So if you perform this synchronization, forbidding reflections, okay, you will discover that there are left teeth and right teeth. Okay, so that's one very trivial observation. So 1, 2, 7, 8, I believe that these are right teeth and these are left teeth. But you can do better. Okay, so here's another set that the anthropologists and the evolutionary biologists look at. So these are 5 primate genera. So now we are talking about meerkats, I believe, or something similar to meerkats. So what's quite remarkable is that these 5 types of animals, they have slightly different diets, and these slightly different diets are reflected on the slight differences between their teeth. Okay, I'm telling you what I learned. Okay, but it stands to reason. And the question is, can you see this? Well, I can't by just staring at it. I can't, but our algorithm can do it. So here's an example of this SynCut algorithm in action. So So we have 5 types of simians. I don't even know what these I can't picture them. So my knowledge of biology is limited to what I just told you. The diffusion map algorithm, it classifies these up to a point, but using the SynCut algorithm, we see clearly 3 groups, and those correspond to what these animals eat. Do they eat leaves? Do they eat fruits? Or do they eat insects? And that's quite remarkable. Just you do this bundle-based geometry, let it loose on animal teeth, and they will tell you they eat different things. And I think this is why we do data analysis. This is really why I do data analysis. It's this amazing connection that you do some geometric topology, and all of a sudden you get this, that these animals eat leaves. That's not what you learn in algebraic topology classes. And and I think, I'm just so happy that we get to learn this, or I'm happy that we get to learn this. And this is all I have to say. So I'll stop here. Thank you so much.
So you have the tooth and you have some points on the tooth. How do you go to a graph with group action?
Yeah, so there are various ways to do it. One of them is, for instance, some Procrustes type matching. Right, so you can, by Procrustes matching, you can find a rotation, for example, that matches one tooth to another as well as possible. In this case, the landmark points are crucial because you can regard each tooth as 16 vectors in R3. So your question is, what's the best orthogonal transformation that matches these 16 vectors to these 16 vectors? Each tooth is a vertex in my graph.
And the group action is this Procrustes.
That's exactly right. So that's exactly that's a very astute question. So that's exactly how it works. In my graph, each tooth is one vertex. In the fiber above this graph, which is R3, a copy of R3, I have those 16 vectors describing the landmark points. So between tooth here and tooth there, I have those 2 fibers, and use, for instance, the Procrustes matching method to find an orthogonal transformation that takes me from here to there, as well as possible. I will, for instance, it might be reasonable to, for instance, demand that I have a transformation of a positive determinant. So, for instance, I may not want reflections or something like that. Or, if I'm interested, so this is when your animals are of the same size. But if you take a meerkat and a whale, and I'm just okay. So you take a meerkat tooth and a whale tooth, and you want to classify this. So then your first. I've actually seen a whale tooth. It's big, and meerkat teeth are not so big. So beyond this trivial observation, if you wanted to study some more functional similarity or differences between them, then you would need to allow transformations at scale, up and down, and so on. So, or you may not. You may insist on isometries, so that you know that a big tooth is different from a small tooth because it may indicate that it comes from a big animal rather than a small animal. Okay, so yeah. The diffusion map, this is a popular way of matching shapes. That's another algorithm that's used in shape analysis. So that's what it is. That's an example of an established algorithm that's used to this. So this SynCut seems to see things a little more precisely.
Can you always take as a graph a tree, and then you will have no curvature, no discrepancy, frustration?
No frustration. There is no frustration on trees. That's exactly right. I don't know. In many cases, it sounds like a reasonable assumption to make, especially if you are if you're interested in evolution and study something like phylogenetic trees, then eventually beyond perhaps some place where you have loops, you may find yourself in a tree-like situation. So yes, it's possible. There is no frustration on trees. So
Just a question, like, because you mentioned that, for example, the size. So do you know that these animals, the different eat different things, they have the same size? Maybe you pick up the size of the teeth.
they just happen to be of similar size. They are roughly the same size. So yes, I believe that the teeth I showed you here are roughly as we would expect. You know, so there are slight differences in sizes. I believe that these are to scale. So at this stage, the question was, can you see enough of the difference to be able to classify them according to some function? And the answer is yes. But the whale and the meerkat, that's an interesting question, right? There's somehow, do we care about the difference in scale or do we not? And depending on your point of view, there will be a different class of transformations that you can consider.
So did you use the simplicial complexes or just the landmarks?
Just the landmarks. You can be fancier. You can try to take a larger class of transformations by using the mesh provided, but we haven't done it.
Do you think you would be able to do it as well with just the simplicial complex without the landmarks?
It's a question of computational complexity, I think. The story I told you will still work, because all I want is some transformation from some group I can describe. Between they will take one object to another object. Okay, if you want me to preserve to find a simplicial map from one mesh to another, I believe it's doable, but it may be difficult. And just looking at the landmarks seems to provide interesting information. But it's a question we are considering. I mean, how do you enlarge the class of available transformations? So that's, to us, that's a question of, if you like, a class of transformations that you want to consider.
How does it compare to machine learning?
Oh, I don't think you can do it by machine learning. I mean, I don't know enough about the the machine learning approaches to shape analysis, but I trusted Cheyenne when he said that this is better. So.
Okay, so if there are no more questions, let's
Thank you. Thank you very much.